Yesterday we introduced the idea that acids react with bases, and when they do, they make neutral products. So neutralization is simply a reaction between an acid and base to make neutral products. So this is a general layout of that reaction. We have an acid plus base makes salt and water. Water comes from the hydrogen of the acid and the hydroxide of the base joining together. This is a double replacement reaction. So for example, the hydrogen and the sodium in this particular reaction will switch spots. That means hydrogen gets with hydroxide, HOH making water. And then sodium will get with chlorine to make NaCl. Now remember, when we do such reactions, if there are little numbers, like if there was a little 2 right there with the sodium, we do not carry those over because the little numbers will change. Once we make an ionic compound, we have to balance the charges of those ions. So it will be helpful if you guys have your periodic tables out to find those charges. Sodium is in column 1A, so that's a charge of +1. And chlorine is in column 7A, so that's a charge of -1. A +1 and a -1 balance, you only need one of each anyway. The very last thing you would do is balance the reaction as a whole with the big number coefficients. We always do that after we balance the charges of the salt that we make. So, for example, in this reaction, barium is going to switch locations with the hydrogen. That means H gets with OH. And I totally ignore this 2 here because those little numbers, remember, don't matter. So whenever H gets with OH, that makes water. Barium gets with nitrate to make the other product. That's our salt. It's simply an ionic compound. However, we do carry that little 3 over because that's part of the polyatomic ion nitrate. That's who it is. So we got to bring that little 3 over. We now have to balance the charges of the salt. So barium has a charge of +2, and nitrate, you could tell, is -1 because it's only bound to 1 hydrogen over here. Therefore, the formula has to be a NO3 2. We need 2 nitrates to balance out the charge of barium. From here, now we can balance the reaction as a whole so that we have the same number of each element on the left side of the arrow as we do the right side. So right away, I notice that I have 2 nitrates on the right side of the reaction, so I'm going to need 2 on the left side. Now to figure out my hydrogens, I have them in 2 different compounds. I have 2 hydrogens in this compound and another 2 here. That makes 4 total hydrogens on the left side. So in order to get 4 hydrogens on the right side of my equation, I'm going to need 2 sets of waters, because 2 sets of 2 will give me 4 hydrogens. And now this reaction should be completely balanced. We have 1 barium on both sides, we have 1 oxygen on both sides, we have 4 hydrogens on both sides, and we have 2 nitrates on both sides. I'll do the next one with you guys as well. So hydrogen and calcium are going to switch locations. And just as a side note, I know this is double replacement reaction because I have 2 compounds. So the H and the calcium switch spots. Whenever H gets with OH, regardless of these little numbers, that makes water. And calcium and bromine are going to get together. We must determine the charges of these 2 ions to make sure the formula is correct. So calcium is 2+. Bromine is -1. Therefore, this should be CaBr2. All right, now we can balance the reaction as a whole. I notice again right away that I have 2 bromines on the right side, so I'm going to need 2 bromines on the left side. If you count your total number of H's on the left side, I have 2 from HBr and another 2 from calcium hydroxide. That creates 4 H's on the left side, so we're also going to need 4 H's on the right side. Now would be a good time to pause the video to try the next 2 reactions out. All right, it's just a coincidence that water had a 2 in front of it every single time. That's not always the case. It was not the case up here. Sometimes it can even be a 3. Okay, so that's how we predict the products of neutralization reactions. Now what we're going to do is use these reactions to our advantage. So what we can do with these neutralization reactions is stoichiometry. I know it's our favorite. But essentially, we can use this mole ratio of acid to base to determine the concentration of one of those solutions. So like if you don't know how acidic your rainwater is, you can react it with base. And if you know exactly how much base was involved in the reaction, you can figure out how much acid is in your rain. We'll be using molarity often, the molarity equation often, to find that concentration. So let's just do a little bit of practice before we get into a big problem. So molarity's equation has to have the volume in liters. So if you give it to it in milliliters, to convert it to liters, remember you divide by 1,000 or move the decimal place 3 times to the left. So 500 milliliters is 0.5 liters. If you have 25 milliliters and you want to put it in liters, again, move the decimal 3 times to the left. This is be 0.025 liters. All right, some more molarity practice. So you see a solution bottle is 0.2 molar. In the lab yesterday, you guys used 0.1 molar. That's simply its concentration. It's how many moles there are in a liter. So you could say it's its concentration, or you could say like in every 1 liter, there are 0.2 moles of HCl. So it's just how concentrated it is. Okay, how many moles of HCl are in 500 milliliters of a 0.2 molar HCl solution? We can use the molarity equation for this problem. So molarity is moles over liters. I'm going to solve for moles, so that's like my X that I don't know. They tell me I have 500 milliliters, so that would be 0.5 liters, moving the decimal place 3 times to the left. And 0.2 molar, that's my big M, that's my molarity. So I have everything I need to solve for moles. I'll cross multiply, so I'll take 0.2 times 0.5. Which would give me 0.1 moles of HCl in that amount of volume. Here's another example of using the molarity equation in a different way. It says if there's 0.09 moles of barium hydroxide in 50 milliliters, what is the concentration? Another word for concentration is molarity. So we're going to solve for big M in this equation. That's our unknown, big M. So big M is moles over liters. There are 0.09 moles, and we need to convert this to liters by moving the decimal place 3 times to the left. So that would be 0.05 liters. So taking 0.09 divided by 0.05, we get 1.8 molar barium hydroxide. Now the next question asks, what is the concentration of hydroxide, though? One thing that these don't tell you is that this is a strong base. Hydroxides tells us it's a base, but it's also a strong base, which immediately you need to think that means it completely gives us all of its ions. So every single hydroxide will come off of each molecule. So if you notice, there's a 2 next to the hydroxide. So every single molecule will give us 2 hydroxides. That's kind of like if every single one of you right now were to give me your shoes. All right, so let's say there's like 24 of you in the room right now, and you give me all your shoes. So that means I'll actually have 48 shoes, not 24, but twice that amount, because every one of you have 2 shoes. That's like the hydroxides here. So my molarity of hydroxide is actually going to be double of 1.8. My molarity of hydroxide is going to be 3.6 molar, because every single one of these molecules gives us twice the amount of hydroxide. All right, I'm gonna stop this video for the first page and I'm gonna have a second video for the next page.